Okay, so yesterday we talked about climate. We talked about the factors that influence climate. We talked about the components of climate. Looking at a climate graph, we can infer where that location might be, what the weather is like, and what factors influence that climate. Okay, so what were the four components of climate again? Right?
Temperature, precipitation, light, and wind.
Temperature, precipitation, light, and wind. Yeah. From a climate graph, there's really no way to infer wind. Okay, there's nothing on this climate graph that tells us about wind. It does tell us about temperature. Okay, that's what the line is. Right? It tells us, what it is by month. It tells us its patterns. And then it tells us precipitation by month. Those are the bars on the graph. Okay? From those two things, we can infer temperature, obviously, precipitation, obviously. We can also infer light. Okay? How can we infer light from a climate graph? Like if the line's flat like this, what did we say that meant in terms of where that thing might be? Right, it's near the equator. If the amount and intensity of light doesn't change, then your temperature's not going to change. But if you get further away from the equator, you start to see a curve in the temperature because you start getting seasons. The effect of the Earth being tilted 23.5 degrees means that your amount and intensity of light is going to change throughout the course of the year. There's going to be parts of the year where you get lots of intense sunshine for hours and hours a day, summer, okay? And parts of the year where you get less hours and less intense sunshine, and so it's going to be colder during that part. So we can infer the pattern of light from the shape and location of the temperature curve, if there is one, okay? So right now, this temperature curve on this graph is pretty low, right? It goes down to minus 10 degrees in the wintertime and only gets up to about 15 or 14 degrees in the summer. Okay, so where that graph is, this graph here, it's got the same curve, but that curve is much higher. The coldest month is 6 degrees Celsius, okay, and the hottest month is 28 degrees Celsius. That tells us that that place is probably closer to the equator, but far enough away that there's still a significant change in the amount and intensity of light it receives. Everyone kind of follow the logic there? Okay. One of the things you're going to be asked to do in this class is interpret a climate graph. So I give you a climate graph and you've got to be able to read it and tell me what the weather in this place is like, okay, from that thing. So what is the temperature doing throughout the year? What is the precipitation doing? What is it likely like there? Is it like a hot desert, or is it a cold desert, or is it a tropical rainforest, or whatever, okay, based on what you see on the climate graph. Okay, so being able to read one of these and get that information is super important. Right? So to that end, I would like you to write down what you think the three components of climate we can get from this graph would be like: temperature, precipitation, and light. Okay, what they would be like. Describe them over the course of a year. Okay, and what you think that area might be like in terms of, let's say, physical geography. Okay, would it be like a desert, a prairie, a boreal forest, a tropical rainforest? Okay, kind of what do you think it would be like? And give me maybe a guess as to where you think this climate graph comes from. Okay, so I'm going to give you a couple minutes. I want you to just write that down, okay? Because this is the kind of question you're going to get, okay? The first thing you do, tell me about the climate graph. What is the weather like, okay, here? And then infer what it would be like there and where you think this comes from. If you were going to describe the temperature of this place, how would you describe it? Is it constant or fluctuating? It fluctuates. Is there a pattern to that fluctuation? There is, right? Like it's a seasonal fluctuation. There's a summer and a winter here. Would you agree? Okay. I mean, in the wintertime, well, northern hemisphere winter, okay, it's January, February, March. I mean, around here, it's more than that, but, okay, it's November, December, January, February, March, that's our winter time, okay? It's below 0 for those times, okay? Down to -10, okay, in December and January. And then we see a pretty steady increase, okay? Temperature goes up into the spring, okay, and up above 15 degrees Celsius, right? And you gotta remember, this is like an average, right? Like for the month. So if there was, some cool days in July, they could skew it. Does that mean this place couldn't get to be 35, 40 degrees sometimes? It totally could, okay? It just, the averages say this much, right? And then we see obviously a decline as we head into fall, right? Now, what we notice in terms of precipitation is that the bulk of the precipitation comes in June and July. Okay, those are the wettest months. Okay, and they're significantly wetter than the others. Okay, upwards of 75, 80 millimeters of rain. Okay, now 75, 80 millimeters, is about that much. That's a pretty good amount of rain. Okay, I mean it should keep things pretty healthy, right? And then we see that taper off. Now, according to this graph, you don't get a lot of precipitation in the winter. Is that necessarily true? Like if they don't get any precipitation in the winter, does that mean they don't get any snow? No. In fact, this place could get a lot of snow. Here's the thing about snow. 10 centimeters of snow is equivalent to 1 centimeter of rain. Okay? And climate graphs always show rainfall equivalent in millimeters. So it can make it look sometimes to some places like winter is very dry. It doesn't mean that we don't get any precipitation in the winter here. They likely do, okay? And they likely get significant snowfall. But snow doesn't represent as much moisture as rain, okay? We get a thunderstorm around here and we can get 20, 25 millimeters of rain in a couple hours, right? It can all fall all at once. You get a big blizzard and you get, like we had this winter, and we had one where we got 25 centimeters of snow. Well, that only amounts to that much rain, okay? It's kind of different, right? Everyone kind of follow there? It seems like, oh man, we get so much snow in the wintertime, but it doesn't add up to as much rain as you think, all right? So definitely the summer months are the wettest months, but this place would obviously get precipitation as snow because it's below 0 in the wintertime. Okay, that's all stuff I would expect you to be able to tell me after looking at this graph. Okay, precipitation tapers off in the wintertime, it likely falls as snow. Okay, that would be something you would want to include. It tells you about the weather in that area. Okay, does that make sense in terms of interpreting a climate graph? Okay, where do you think this is? That's here. That's our climate graph. Okay, we get the bulk of our precipitation in June and July. That's when we get our thunderstorms. That's when we get into our thunderstorm cycle where it's hot and muggy during the day and then it downpours or hails or whatever, okay, in the late afternoon and evening. Okay, the bulk of our precipitation comes June, July, we could say May, June, July, even into August a little bit. Those are our wettest months, okay? And those months it falls as rain. Can we get snow in September? We can snow in May and June, but it can happen, okay? It still counts in the precipitation part. All right, making some sense? Okay, try this one. Okay, I want you to do the same thing, okay? I want you to describe to me temperature, precipitation, light, okay? Give me some inferences about what the weather would be like, the location would be like, and then give me a guess as to where you think this might be. Okay, now, something I want to point out though. Make sure you look at the scale for precipitation and temperature. Don't just look at the shapes. It's possible to make a desert look like a really wet place if you skew the scale for the precipitation, right? Like if you make this 0 and this 5 millimeters of rain, the bars will all go right to the top and it'll look really wet, okay? You've got to look at the scale here, okay? Think about how big 40 millimeters is. Okay, it's not very big, right? So think about that. Make sure you look at the scale. Make sure you look at the temperature side. How hot or cold is this place? Okay, I'll give you a couple minutes. Okay, temperature, precipitation, light, inferences about what this place is like. Okay, physical geography if you can, possible location as a guess. Okay, so looking at this graph, what's the temperature like? It's cold. Yeah, okay, I mean, if we look at the coldest months are dropping down close to -20, okay? Warmest months, they get up to 13, 14 degrees, but more of the year is spent sub-freezing temperatures than above, okay? So would this place be close to or far from the equator? Okay, further than the last one we looked at?
Yes.
I would say that's a safe bet, okay, that this place is further north of the equator, and we would have to specify that it's further north of the equator, okay, than the last one we looked at. It's definitely colder, okay? Is it wetter or drier than the last place?
Try.
A little bit, yeah, a little bit drier. The precipitation's a bit more even, okay? It's not like, you know, in the last one where it was Calgary, so it's on the prairies, okay, where it's definitely summer is wet and winter is dry, okay? This is, obviously precipitation is a bit later in the year. There's more in the fall, okay? Because there's probably just more moisture available, okay? And then spring is actually quite dry in this area. And again, most of this is gonna fall in the form of snow because it's cold most of the year, okay? So if it's north of Calgary, it could be, like, is this like Edmonton or further north, like Fort McMurray, or further north than that? What do you think? Whitehorse, way further north. Okay, I mean Edmonton, Fort McMurray. Yeah, Fort McMurray's colder, but it's not as bad as this. Okay, Whitehorse is a lot further north. Now, what can we infer about light from this? Okay, we see a definite drop off in temperature. Does that have to do with the amount of light this place receives? Yeah, okay. Whitehorse is in that part of the world where there are dark days. Many of them, where the sun basically doesn't come up, okay? The sky might lighten a little bit, okay? But you might only see like the top of the sun do this little arc across the southern sky, and that's it, okay? And then it's dark for 22 hours, okay, of the day, right? So that's significantly gonna affect your temperature. Okay, let's try that one. Okay, same thing. Give me temperature, precipitation, light, okay, and physical geography, inference, location guess, okay? All right, one of the reasons I put this one up is to reiterate a point I made before about checking the scale, especially for precipitation, okay? Look at how high that scale goes. It only goes up to 40 millimeters. About that much, okay, in a month. That's the wettest, in fact, it's a little less than that, it's more like 37, okay? That's the wettest month here, okay? And there's some months where, you know, it's less than 5. That's basically, that doesn't get any rain basically that month, right? So is this place wet or dry? Dry, but they skew the scale and make it look wetter than it is because the bars are really tall, okay? It's something you really have to watch for when you're interpreting a climate graph. Like, we're using our graphing skills here, right? Like, we learned how to do these inferences from a graph back in the last unit, okay? I keep telling you, the graphs are everywhere, right? So we look at this graph, we say, okay, the precipitation is actually lower, okay? 40 millimeters is not very much rain, especially in a month, and that's your wettest month. Okay, now there's definitely a really dry part of the year, and it appears to be in, well, that would be June, okay? July and August maybe are a little bit wetter, September not bad, but wetter in terms of you go from this much to this much. It looks like a lot more than it is on this graph because of the scale. Then we look at temperature. Hey, this place never gets below freezing, right? The coldest month is about 11 or 12 degrees. The hottest month is like 34, okay? So, desert, right? Probably like cactus and, you know, scrub and stuff like that. It's certainly not gonna be a vibrant green place given that kind of temperature. And the worst part of it is the hottest time is the least amount of rain, okay? Or at least for part of it. So, this place could get cooked pretty good, right, in the early spring, right? Where do you think it is? I mean, it's still far enough from the equator that it's got seasons, right? There's a cooler part and a drier part.
I said like Las Vegas or like Arizona, like area.
This is Phoenix. Yeah, so Arizona, good guess. LA would look similar, yeah. Okay, so yeah, dry, it's a desert, but it's a mid-latitude desert. That's what we call Arizona. It's a mid-latitude desert. There's a ski hill in Flagstaff, Arizona. Okay, there's places that get cold enough for that. But it's dry, right? That's the kind of thing we have to be able to infer. Describe what you can read, okay, make some inferences, and then take a stab at the location. All right, try for that one. Okay, on this graph are there distinct seasons, and by seasons I mean a winter or summer. Do we see that? Temperature's pretty level, would you agree? Okay, like the coldest month, okay, if we're just looking at the highs, the coldest is 30 and the hottest is 35. Okay, that's very little change between summer and winter, so they don't really have any seasonality, other than maybe wet and dry. Okay, they would have a wet season and a dry season. We can clearly see that. But look at the scale. Okay, the wettest month here is 500 millimeters. That's half a meter of rain in a month. That's a lot. Okay, now when you look over here, it's like, well, yeah, but they got a dry season. But again, look at the scale. The dry season is still getting as much as Phoenix got in its wettest month. Okay, so it's not like it's dry, it's just dry for this place. Okay, would this place be fairly tropical?
Yes.
Okay, what kind of like geography? Is it going to be desert or a rainforest?
Rainforest.
I'd say probably a rainforest, yeah. I mean, you could also maybe say, you know, something more like savanna, like, you know, maybe North Africa or something like that, but definitely this is equatorial, okay? And definitely wet, okay? So, it's Manila in the Philippines, okay? Basically sits on the equator, right? Gives you a pretty good idea of the weather there. Okay. What's different about this one?
Has different seasons. But like, so it's on the other part of the world.
Yeah, it's some other part of the world, not in this hemisphere. Okay, the seasons are reversed. All right, so this is you go to the beach at Christmas kind of a place. Right? Now, fairly wet. Okay, precipitation is even, but it's also fairly high. Okay, the driest month is, well, about as much as our wettest month here. Okay, and then the wettest month is, you know, it's a bit more, but the precipitation here is pretty level, and it actually looks like their winter would be the wettest time. Okay, are they getting much snow here? None, right? It's always above zero here. The coldest month is about 12 degrees Celsius, and the warmest month is about 20. Okay, now there's seasons, but the seasonal change is mild. So that means either it's close to the equator or close to a what? What else could regulate and soften your seasonal changes? You're an ocean. Factors that affect climate. That's the other kind of thing I'm going to want you to work in here, okay, when we're interpreting climate graphs. What are some factors that might affect the climate here? Well, there's seasons, but the seasonal change is soft. That means maybe it's next to a large body of water, like an ocean. Okay? So this, I believe, is Christchurch, New Zealand. Okay? So they have seasons there, for sure, but it's rainier. Okay? It's quite a, actually, like, lush kind of place. But it's not brutally hot either. Okay? Still in the southern hemisphere? Okay, are the seasons a little bigger? Like the seasonal change a little bigger? Okay, so probably further from the equator, okay, and maybe less influenced by a big body of water. You know, there's definite seasons here. Winter it doesn't get below freezing, but it's definitely colder than summer. And the wettest part of the year is definitely in the winter time for this place, June, July, and August. Okay, but it gets pretty dry in the summer in this place. What do you suppose this might be? You know what? Australia would probably be a little more, depending on what part, would be a little drier. okay, especially if you're in the outback, in the central Australian outback. Okay? This is actually Santiago, Chile, South America. Okay? They get a definite warmer summer there with less precipitation. Okay, are we back to the northern hemisphere? Okay, distinct seasons. Right, like there's a pretty significant seasonal change here, up to 25 in the summer, around 0 in the winter. Precipitation's pretty level. Okay, if you have level precipitation, it generally means you can support more complex plant life. Okay, around here on the prairies, it's wet in the summer, it's cold and dry in the winter, so we get grass. Okay, maybe a few trees here or there. But a place like this could probably grow a more complex forest because it never has to endure a long period of drought. Okay, everyone kind of follow me there? Would this place get snow? Yeah, it might. In fact, if it gets snow, because it doesn't get super cold, it's going to get the heavy, wet kind. Okay, like we get in March, right? Like our snow in December and January is like dry, right? Like it's water. That's a weird thing to say, but it's like powdery, okay? And it collects and whatever, and we don't get much out of it until it starts to melt, okay? But this place would probably get heavier, wet snow, right? But the precipitation is pretty level, okay? Temperature definitely far from the equator, but not like, you know, White Horse far. Would it be further south than us? Either further south than us or near an ocean, okay, something like that. This is New York. Okay, if I showed you one for Toronto, it would look quite similar. Okay, Ontario has that same kind of complex deciduous forest that is in New York. Okay. All right, we getting the hang of that? Okay, just interpreting climate graphs. I mean, tomorrow and Friday we're going to be working on that some more. Okay, what I want you guys to find now, please, is lesson 3. Okay, lesson 3's theme is all things come in threes. We're going to talk about all kinds of threes today. Okay, so the big theme of today's 3. Okay, lesson 3, environmental triad, 3 methods of heat transfer, 3 fates of light. Yeah, it's going to be a day of threes. All right, so if you can find that, I'll give you a sec, and then we'll get going on here. Okay, so in this unit, our big focus is energy in global systems. Okay, so looking at energy in terms of like the entire world, the entire Earth. Okay, how does it move about? Where do we get more of it? Where do we have less of it? Second law of thermodynamics is going to come into play a whole bunch in this unit. Energy always moves from hot to cold. Okay, that kind of stuff. It's all going to be a big part of this. Today we're going to look at the mechanisms and the parts of those mechanisms for transferring energy from point A to point B on Earth. Okay, so we're going to look at the 3 parts of the Earth first. Okay, the Earth is broken up into lithosphere, that's the rocky solid part of the Earth. The hydrosphere, that's the water, all the water, okay, ice, liquid water, water vapor, okay, the hydrosphere, and the atmosphere. Okay, obviously all the gases that surround the Earth. Okay? The atmosphere is our biggest focus. The reason for that is the atmosphere is most responsible for energy transfers on Earth. The reason for that, it's the most fluid of the 3 parts. Okay? Obviously rocks are not fluid. They're solid, they don't move around. Okay? They're not going to be transferring energy from one place to another. It doesn't go through the rocky part of the Earth. Okay? Now the hydrosphere, it's got a role to play. It's fluid and it changes state. Solid, liquid, gas, it's got a role to play, but it's nothing like the atmosphere. The atmosphere is constantly in motion. Okay? It connects all parts of the world together. That's going to be what we focus on in terms of energy transfers because they all go through the atmosphere. Okay? Second point there, understand how energy on Earth is absorbed, used, and reflected. We also sometimes use, in place of used, we also use converted. Okay? And then understand how the energy and the Earth interact to produce the conditions necessary for life. Okay, we kind of touch on that a little bit. Okay, but obviously this is kind of the big thing here. Okay, everybody all right with that? So we're going to look at like how the energy, when the energy gets to the Earth, what happens to it? That's going to be a big focus of today. Okay. All right, so the atmosphere. As I said, the atmosphere plays the biggest role here in terms of transferring energy around the Earth because it's the most fluid part, right? Now, there's layers to the atmosphere. Do not memorize the layers of the atmosphere. I could not care less whether you know the layers of the atmosphere. So this diagram, it's just there for an illustration purpose. Okay? What we're most concerned with in terms of energy is the lowest parts of the atmosphere, because the higher parts don't have enough gas to really do anything in terms of energy transfer. Okay? They're important in that, you know, that's where the ozone layer is, which protects us from ultraviolet radiation, and where the Van Allen belts and the Earth's magnetic field are, because that protects us from the really nasty stuff the sun spits our way. We got to see it in action the other day, a couple weeks back when we had the really good auroras. Okay? That is like watching the Earth's protective shield do its job. Okay, what you're literally seeing when that happens is really awful stuff that the sun has spit out, okay, striking this giant energy shield, okay, that protects the Earth. Okay, the light that we see is the result of these particles being stripped away by the intense radiation and solar plasma that's hitting the Earth. Okay, rather not hitting the Earth, hitting the Earth's shield and keeping us safe. Okay, so when you see that, you know we're good. If you don't see that, you might be frying. And that's bad, because literally that's what can happen if you don't have a magnetic field. Okay, so that's all up top here. We're not really concerned with that for today. Okay, what we're concerned with is what goes on down here, okay, in the lower parts of the atmosphere that are more dense. Okay, now, dense air is important. The air, the atmosphere here provides us with something called atmospheric pressure. Okay? The lower you are, the higher the pressure. Okay? And atmospheric pressure keeps our bodies working properly. Okay? And it also, the more dense the atmosphere, the more it can move around. So, in terms of our survival, we live in the troposphere. There are only a couple of points on the Earth's surface that you could stand on that would be in the next layer up, the stratosphere. That would be like the top of Everest, the top of K2, any mountain high enough to be in the death zone. Okay, anyone heard that term before? Okay. The death zone is a term that climbers use to describe areas above a certain altitude, 10,000 meters roughly. Okay. You get up there and you can only live there for a few days. It doesn't matter what you do. You cannot survive there long term because the atmospheric pressure is so low that you cannot metabolize oxygen and sugars and that kind of stuff because there isn't enough oxygen. But secondly, there isn't enough pressure to keep the gases that are normally dissolved in your blood properly dissolved. And so they begin to escape. Okay? Water begins to accumulate in your lungs because there isn't enough pressure to push it back into your bloodstream. And you get what's called pulmonary edema. It's basically pneumonia, but without the bacterial infection or viral infection that causes it. Your lungs fill with fluid. Okay? There's also the problem with the lack of oxygen. Your body just doesn't metabolize things properly, and you get really tired. Okay? And that, in the end, is what kills people on the top of these mountains. Okay? They get hypoxia. That is, there's just not enough oxygen. Their brain stops working correctly. Their body's not burning sugars properly, and they get tired, and they just go, I'm tired. I'm just going to lay down here for a few minutes. And they don't wake up. Okay? That's just how things go, okay, on the top of those kind of mountains, right? It's grisly, but they actually use the bodies of dead climbers as markers on the way to the top of Mount Everest. Okay? They know how far they are from the top by which body they're at. It's really grisly. Okay? Like, there's this place called Green Boots Cave. Right? Some guy wearing green boots crawled in there and died one time. And you're not going to decay or decompose at that altitude, so he's just there with his green boots. He said, oh, it's green boots. Okay, well, we're 4 hours from the top now. Okay, and off you go. Yeah, but it's when you get to that altitude, the human body just doesn't function. Okay? The atmospheric pressure is so low that water boils at 65 degrees. Okay? These guys are literally making soup in their tent, and they're eating it while it boils. okay? Because there's so little air above it that water can evaporate at a much lower temperature, okay? On Mars, if you went out on Mars, you just take water out there and it would evaporate. You wouldn't even have to put a heat source to it. There's just not enough atmospheric pressure to keep it a liquid. Okay? Does that sort of make sense? Okay? So we don't deal with the parts of the atmosphere that don't have enough pressure to do anything. We're going to deal with the lower parts where there's lots of air, lots of ability to transfer and move air. Okay? Okay. So, super important slide. Okay? When we're talking about light and energy coming to the earth, okay, we are concerned with how much of that light is being absorbed, how much of that light is being reflected, and how much of it is being converted. Because those are the three things that can happen to light. We call them the three fates of light. Okay? The three fates of light when it comes to the earth are it could be absorbed, it could be reflected, or it could be used or converted by plants in photosynthesis. Now, incoming solar radiation hits the Earth's atmosphere. Stuff starts to happen. The atmosphere is made of matter. When light and matter interact, things happen. Okay? One of the things that can happen is reflection. Okay? If it's hitting the top of a cloud, okay, tops of clouds are white, they're highly reflective, and energy just bounces off. If the energy bounces off, do we gain any energy? No, it bounced off. You have to absorb energy, okay, in order for your energy to go up. So reflection doesn't help us very much unless we're trying to stay cool. Okay? So that's why in the summertime we typically wear lighter colors. Right? If you go outside on a hot day and you're wearing a black shirt, you're going to be hotter because black absorbs lots of light. Okay? But if you're wearing a light colored shirt, okay, you're going to feel cooler. Okay? In the parking lot on a sunny day, if you got a white car and a black car, you can barely touch the black car, it's so hot, but the white car is still cooler because it's absorbing, it's reflecting more, okay, than the black car is. All right? Now, some of the incoming solar radiation gets what we call backscattered. Okay? That means that certain wavelengths of light hit the atmosphere and they get reflected, but not like straight back. They get randomly reflected. That's scattering. The wavelengths that typically get scattered by our atmosphere are blue. That's why the sky is blue. Okay? I know somewhere along the way some well-meaning science teacher told you the sky is blue because it reflects the ocean. The ocean is clear. Okay? Water is transparent. It is not blue. The ocean is blue because it reflects the sky. It's actually backwards. Okay? The sky is blue because it scatters blue light on normal days. Last year, this time of year, what color was the sky? We had all the forest fires. What color was the sky? Orange. Yeah. Okay? Because particulates like soot and smoke and ash reflect and scatter orange wavelengths. It's why when the sun comes up in the morning and when it sets in the evening, the sky appears orange. Because when the sun is low, it's going through the air that's closer to the surface, which is more dense, has dust, okay, things like that, particulates in it, okay, changes the sky to that color because it gets scattered by different kinds of air, basically. Does that sort of make sense? Okay, that's why our sky was orangey brown, okay, highly polluted areas. Okay, if you were like in a city, like a big city in China, like I've seen pictures of it, like there's so much pollution in those areas that the sky is brownish orange kind of all the time. Okay, so it all depends on what your atmosphere is made of. If you've seen any pictures from like the Mars rovers, the sky on Mars is like red. Okay, it's like brownish red because it's got mostly carbon dioxide. Okay, it's just made differently. Everyone okay with that idea? Okay. So backscattering, that can happen. That represents basically just a loss, right? That doesn't change the energy, it's basically reflection. Now, as the solar radiation comes through the atmosphere, some of it might get absorbed, okay? If we got darker colored materials in the atmosphere, it'll be absorbed a little bit by those materials, okay? But it's eventually gonna hit the Earth. Now, when it hits the Earth, one of three things can happen. It can be absorbed, it can be reflected, it can be converted by plants. Okay, so that's going to depend on this. Okay, the word albedo, super important term for this unit. Okay, albedo is the reflectivity of the Earth's surface in a given location. Right? A high albedo means lots of reflection. A low albedo means lots of absorption. We use this idea, this concept, all the time. Okay? When we get a big snowfall in the wintertime, okay, snow plows go out, okay, and what do they throw on the road? Salt and sand. Okay, they throw sand down, lots of it actually. Okay, that does two things. You know, the rocks in it can provide us a little bit of traction, but does it change the color of the snow? Makes it darker, right? Darker colors absorb more energy. By throwing dirt, essentially, on the snow, we lower the albedo of the snow, and it melts faster. The salt helps that. Okay, the salt lowers the melting point. Okay, or sorry, raises the melting point of the snow. Okay, and all of that stuff works together to clear the roads more quickly. Okay, that's why we throw that stuff down. It's also why last year we were, or scientists were very worried, and there was a lot of additional melting of our glaciers. Last year, with all the forest fires, lots of soot and ash fell out of the sky and ended up on the glacial ice. Okay? Now, that ice is normally bright white and highly reflective. But this layer of ash and dust and soot fell on it last year, and there was far more melting than normal because the albedo of those glaciers came down. They were darker in color, and they melted faster. Okay? I mean, it didn't help that we had very little snow either, okay? But all that deposition of darker material was a big problem. Okay? So that's kind of how albedo works. If we look at like an area around here, let's say, from season to season, in the wintertime, in terms of energy, we're in the worst possible situation. We get only a few hours of sunlight. The sunlight is not very direct, right, because we're tilted away from the sun. And the ground is covered in white snow. Right? White is the most reflective, the highest albedo color there is. Okay? So most of the energy that actually strikes the surface of the earth here in the wintertime just bounces right off. Okay? That's why it stays cold for so long. Okay? Now, we get into the spring, the sun's up for longer, okay, and bits of rock and trees get exposed. Does snow melt more quickly around a tree or around a rock if the rock gets exposed? Definitely does, okay? Next year in the springtime, okay, have a look at it. Okay? If you've got like a tree or something in your yard, the snow around it's going to melt more quickly because it's darker. It's going to absorb more energy. It's got a lower albedo. The temperature around it is going to go up faster. Okay? Everyone kind of follow me on that? Okay. So in the wintertime, 85 to 90% of the incoming radiation just bounces right off. It's gone. Okay? About 10 to 15% is going to be absorbed, and that's just going to be where there's darker stuff exposed. Okay? In the summertime, the situation is almost completely reversed. Okay? Grass, rocks, dirt, etc. is all exposed now. The sun is up for longer periods of time. It's more directly overhead. 70% of the incoming solar radiation is getting absorbed. Only about 10% is getting reflected, and that would be from like light-colored surfaces. Okay? And 20% would be reflected off of like plants and stuff like that. Okay? So 70% coming in, getting absorbed, versus 85 to 90% getting reflected in the wintertime. It makes a huge change, which is part of why it's so much warmer in the summer than it is in the winter. Why it takes so long to get the snow. I mean, we're lucky around here. We get Chinooks that kind of take care of it quickly, but okay, typically it takes a long time to get rid of the snow. All right, everybody understand what albedo is? Okay, super, super important term. All right, something I want you to write down. Okay, I want you to write down here the 3 fates of light/energy. Okay, so here's 2 of them. We'll put the 3rd one on in a minute. These are the 2 that are affected by albedo. Okay, I'll get out of the way here and let you write that down. All right, so the first 2 fates, okay, the first 2 things that can happen to light when it strikes the Earth's surface, it can be reflected. Okay, reflection can occur. If reflection occurs, no energy is gained. Okay, the 3 dots here mean therefore. It's shorthand for therefore, because you know what the 3 dots are. Okay, therefore, no temperature change. So there's no in or out gain of energy there. Okay, the second fate is absorption. All right, if we've got something with a low albedo, then lots of it's going to be absorbed. Low albedo means it's likely darker in color. Okay, that's going to mean energy gets gained, therefore temperature increases. Okay, so those two things are affected by albedo. Right? The third fate is conversion, and that is simply photosynthesis. Okay? Light strikes plants, plants can convert the light directly into sugar, into chemical energy. So here's where we're going with the 3 fates, what you'll be asked to do. On a unit exam, I would give you a question like this. I would take a Google Earth satellite photograph of an area on Earth. And I would give you a description of that area along with it. I tell you where it is, okay? And what you'd be expected to do is look at that picture and read the description and then be able to tell me what's going to happen to the light that strikes that area. How much of it do you think will be absorbed and why? How much of it do you think will be reflected and why? When you're talking about that, what word had better be in your explanation? Albedo, okay? Because that's what determines how much gets reflected and how much gets absorbed, okay? And then also talk about whether you think conversion will happen and maybe how much of it, right? If I show you a picture of, a glacier, well, you're probably not going to have any conversion because no plants grow on a glacier. Okay? And you probably have a lot of reflectivity because glaciers are light in color and it will reflect a lot of the energy away. But maybe there's also a dark rock in that picture, and you could say, well, the dark rock, that'll absorb some energy because it has a lower albedo, and maybe the snow around it or ice around it will melt more quickly. That's what I would expect you to be able to do. Does that make sense? Okay? That is, take these 3 fates and apply it. You're going to find that a lot of the questions in this unit work like the biology questions. Here's some knowledge. Take it and apply it to this. Okay, so there's going to be a lot of that application. Thank you for grab your phone. Okay, so everyone understand how I'm going to ask about that? Okay, it's simply application of knowledge, okay, for this. All right, so the atmosphere, like we said, its role is to, get the energy through, and then once it's absorbed, then it can be moved around. Okay, and the atmosphere is responsible for moving energy around. Okay, with what would we call moving air? Wind. Yeah. Okay, the atmosphere's main mechanism for transferring energy is wind. Right? Wind happens because of the second law of thermodynamics. Energy is going to go from hot to cold, and it also is influenced by pressure. You have areas of high pressure, areas of low pressure. Air naturally wants to achieve a balance, so it's going to move, okay, in that way. It's going to take energy with it, right? And it's also going to take moisture with it. Okay? Moisture is representing a different kind of energy, which we'll talk about here in a minute. Okay? Now, in this one here, it also talks about some of the gases and things like that. I'm not worried about whether you know about what gases are greenhouse gases. Okay? Greenhouse effect, is it important? Is it bad? See, and that's the thing, is actually having a greenhouse effect isn't bad. Having one that's getting worse, yes, that's not good. Okay? But if Earth didn't have some greenhouse effect, it would be an ice ball. And it has been in the past. Okay? Very early on when the first photosynthetic bacteria appeared on Earth, there was nothing to eat them. They just went crazy. And they radically changed the composition of the atmosphere to the point where there was almost no carbon dioxide in it, which lowered the greenhouse effect down to the point where Earth entered a massive, millions of years long ice age called snowball Earth. Okay? So we need a greenhouse effect. It's important for regulating and making temperatures habitable. Do we want it to get really bad, like what we're doing to it right now? Is not good. It's getting worse. Okay? If not the worst it's ever been in Earth's geologic history, but it's changing things, and we have a part to play in that for sure. Okay? But having a greenhouse effect is not bad. Okay, and that's the problem with it, is everyone's like, greenhouse effect, ooh, that's terrible. No, it's not. Okay, we don't want to be like Venus, the massive greenhouse effect that makes the surface of the planet feel like the inside of your oven on the self-cleaning cycle. Okay, we don't want that. But on the other side of it, Mars has so thin of an atmosphere that it has no greenhouse effect, and it's cold. Okay, so you got to have that kind of Goldilocks, it's just right kind of amount of greenhouse effect. Okay, and that's of course caused by carbon dioxide, we know that. Okay, methane is another greenhouse effect gas. It's produced by bacteria and farts. Okay, so it literally is fart gas. Okay, ozone. Okay, the ozone layer is important, protects us from ultraviolet radiation. Nitrous oxide is in there. Okay, all that stuff. Yep, they play a part. Solar radiation can get through them on its way in, but when it bounces off, it doesn't get back out, so it bounces around a few times and makes it warmer. Okay, oh, I had this picture here, I found it the other day. It's the rain, remember the rain shadow, the mountains that we talked about the other day? Okay, well, this is kind of a picture of it. This is, again, Mount Robson, okay, in the Canadian Rockies. And every once in a while, you'd just get me like perfectly clear, and then all of a sudden a cloud would appear. Okay, and what was happening is moist air was moving along, but all the moisture was vapor. And then it hits the mountain and tries to go over it, and as it goes up and over, you can literally see all the moisture just comes out of the cloud, out of the air, falls on the top of the mountain as snow, and then there's basically nothing on the other side. And you could actually watch it happen, so that's kind of that rain shadow effect, but you can see it literally happening as moist air tries to go over a tall mountain. Okay, I'm gonna give you about a 3-minute break here, and then we're going to talk about the hydrosphere real quick. Okay, so 3 minutes, you can answer all your important snaps, okay, and then we'll get back to this. We talked about the atmosphere. Atmosphere has the biggest role to play when it comes to transferring energy because it is the most fluid part. It moves the most easily, and it's connected to all parts of the earth. Okay? Second to the atmosphere is the hydrosphere in terms of its effect or ability to transfer or transport energy. Okay? Now, obviously, we've got a lot of water on Earth, okay? But 97% of it is in the ocean, right? 3% of it is fresh. Now, if we look at how much of that fresh water, okay, how much of that 3%, okay, is actually liquid, it's not a lot of it, okay? About 1%, okay, of the water that's on Earth is actually like groundwater that we can tap with a well and drink, okay? Ice caps and glaciers represent more than 2/3 of it. Now that number is unfortunately shrinking, but okay, they still, a lot of the water on Earth is in a solid form. So we're most concerned with the liquid water on Earth, which means we're most concerned with probably the stuff that's in the oceans in terms of its ability to move, become a vapor, okay, and become precipitation somewhere else. All right? How many times have you learned the water cycle in school? Like, somebody's been beating you over the head with the water cycle, like basically every year in science in your whole school career. Okay, one more time. We're gonna go over the water cycle here. Okay, you need to know the parts of the water cycle. So evaporation, transpiration, condensation, precipitation, infiltration, and runoff. Okay, you gotta know those parts, be able to see them on a diagram. But what we're more concerned with in Science 10 is where does the energy get involved in the water cycle? What parts of the water cycle are taking energy? What parts of the water cycle are transporting or moving energy? And which parts are letting it out? Because the water cycle actually plays a huge role in moving energy from the equator to more northerly parts of the world. And the way that it does that is in water vapor. Okay? Does it take a lot of energy to evaporate water? It actually does. Whoa. 2,260 joules per gram. Okay, so 1 gram of water is 1 milliliter of water. Imagine a volume of water about the size of a raisin. That's 1 gram of water. Okay, it takes 2,260 joules of energy to turn that liquid water into water vapor. That's huge. Okay, now imagine a thunderstorm comes along. How much water is in a thunderstorm? Hundreds of thousands of liters, probably. Okay, I mean, you think about it, if we get a big hailstorm and the hail's all in the gutters everywhere, right? It's just running through the streets, they're flooded because the drains can't take it all, okay? It's a lot of water. Well, it's a lot of energy too. There's a lot of energy in a storm. Okay, that's why they can be so damaging. Sometimes there's so much energy that it has to get out in the form of a tornado, in the form of kinetic energy. Okay, there's huge amounts of energy in water vapor. Okay? So if water evaporates from the ocean and it moves over the land, we're not just seeing transportation of water, moisture, but we're also seeing a movement of what we call latent heat. Okay? Latent heat is heat you can't feel. Okay? Sensible heat is the heat we feel. Okay? You're up next to a fire, you feel the sensible heat coming off of it. Okay? Latent heat is heat that's stored in water because it's changed state. Okay? Even liquid water stores energy. Okay? It has to lose it in order to turn into ice, in order to freeze. Okay? But when we're talking about huge amounts of energy, it's present in water vapor that can move through the atmosphere, okay, as latent heat. All right, so in the water cycle, okay, evaporation and evapotranspiration, so these two processes, that's liquid water turning into a vapor, either directly from the ocean or from plants as they carry out photosynthesis. That's also a big part of it. That takes energy. Okay? So these two processes here, those are energy in. They require energy. Okay. Once they've happened, then that energy can move. Okay? That energy is latent heat. Right? So that energy moves from wherever the water was evaporated, okay? And we've already talked about how, if water evaporates from one place, it's not falling directly back down on there. Okay, like whatever evaporates from outside today is not falling back down here in another day. Okay, it's going to go somewhere else. Right? So that water vapor moves because of wind, because of the second law of thermodynamics, whatever, it goes somewhere else. When it condenses and falls as precipitation, that's energy out. Okay? And we see that in a thunderstorm. That's the best example. Okay, of seeing the latent heat that's in water vapor being released rapidly. Okay? We don't necessarily feel heat coming off of a cloud. Okay? In fact, it often gets cold right before it hails. Okay? But we're seeing that energy released rapidly in the form of precipitation. Okay? So the rain just dumps out, or the hail just dumps out on us. Okay? High winds, kinetic energy, lightning. Okay? All that stuff is that energy that's been taken from somewhere else trying to get out. Okay? And trying to get out fast. Okay? Does that sort of make sense? Okay? It's where we can see the actual effect of that energy being released. Right? There's also some energy here in runoff. Okay? When water's up at a high altitude, okay, like in a glacier or a lake or whatever, it also has gravitational potential energy. When it starts to run through the river, okay, it's turning that into kinetic energy. Can we harness that? That's what hydroelectric dams do. Okay? They're taking energy that was evaporated, okay, and taken somewhere else, and it fell on a mountain as snow, and it got stored there for years and years, okay, until it started to melt. Okay? And then it released that mechanical energy. All of that represents energy that came at one point from that water. Okay, now it's somewhere else. Okay, so that's how the water cycle moves energy. That's what you need to know about the water cycle in grade 10. Okay, where's the energy in this water cycle? Okay, another thing to talk about here. Okay, so this is another picture I took before you were born. Okay, this is the Robson Glacier. Okay, so it's on Mount Robson. It's the Robson Glacier here. Now, in terms of like absorption and albedo, it's white generally. Highly reflective? Okay. But are there parts around it that are darker? Okay. And in fact, like we said, even the snow itself looks a bit dirty. okay? It's got a lower albedo than it probably should, okay? When we did this climb, okay, we got to a meadow, and in the middle of this meadow, where there was no snow, no ice, there was a sign. And the sign said, "The Alpine Club of Canada marked this point as the toe of the Robson Glacier in 1902. Okay? I took this picture in 2003. I had to hike 4 kilometers before I got to the toe of the glacier. Okay? In 100 years, that glacier shrunk 4 kilometers, and that's just in length. Okay? 100 years ago, this glacier wasn't just longer, it was deeper. Okay? You start getting that rock exposed, you start getting stuff falling on that ice, and it's going to melt faster. Okay? And that's what we're seeing. Okay? That's why environmentalists are so concerned. Okay? They realize that this represents a lot of water. It also represents a lot of energy. Okay? And we want to try and preserve it. Okay? There are things we have to be mindful of in that way. Okay? All right. Okay, last bit here on the lithosphere. Okay, so the lithosphere is the solid part of the Earth. So when we're talking about the 3 fates of light, okay, the 3 fates of light are influenced by the lithosphere. Okay, it's the albedo of the lithosphere that determines how much of it gets reflected, how much of it gets absorbed, and the lithosphere provides soil for plants that do the 3rd fate of light, which is transformation, conversion, use, photosynthesis basically. Okay? Without the lithosphere, that doesn't happen. Okay? I mean, there's algae and stuff in the ocean as well, okay? But we're talking just about the terrestrial part here. Okay? So soil is a big part of this. Okay? All right, so the lithosphere doesn't have basically any role to play in transporting energy from one place to another. Solids don't generally, like rock, doesn't conduct heat from A to B very well. Okay, not like if you put a metal spoon in soup, right? Like you don't want to have it in there very long, or the spoon will get hot. Okay, metals conduct heat very well. Rocks don't. Okay, so the lithosphere doesn't play a role in transportation or transfer of energy. It plays a role in capture. Okay, if it's dark in color, it's got a low albedo, it'll absorb it. Okay, if it's covered in good soil and there's lots of plants, it'll convert it. That's the role the lithosphere plays. Okay, how many people have ever dug a hole before? Okay, if you don't have your hand up, you haven't lived. You got to dig a hole. Okay, at some point in your life, you got to dig a hole. It's just something you got to do as a human being. Dig a hole. Okay, holes are cool, and they have only one natural enemy. What's the natural enemy of a hole? The pile. Right? Because the pile can fill the hole. It's true. Think about it. Okay? When you make a hole, you also make a pile. You always make them at the same time. Okay? Now, when you dig a hole, what do you see? Dirt. Okay. What do you see in the hole? If I look inside the hole and I see the dirt, is there like any patterns? There's layers. Right. There's layers in the soil. Okay? Those layers are important. All of them play a different role. Okay? I know a bunch of you are going, you're so weird. He's talking about digging holes. You've got to dig a hole. Okay? I've dug lots of holes. Holes are cool. Okay? So soil's the topmost layer of the Earth's surface. It's the layer in which plants grow. It's also the one that determines albedo. Okay? And it's got layers. Now, is this soil? I see a bunch of rocks. Okay? Is that soil? It is. There's something growing in it. Okay? Now, I wouldn't say I'd want to plant my garden there. Okay? Not probably the greatest soil, but it's good enough for that mesquite bush, okay, to grow. Soil is different everywhere you go. Where does soil come from? That's not a question that's easy, is it? Okay? Soil comes from the erosion and weathering of rock. And once you start to get a little bit of soil, stuff can grow in it, which will build up the organic layer and part of soil, okay, which eventually comes to make dirt like we know dirt. Okay, like when you dig a hole around here, you see the topsoil, which is weathered rock and organic material. Okay, and then there's a layer underneath. What layer is underneath? Whenever you dig a hole, what's underneath the topsoil? Doesn't matter where you dig a hole. Clay. Yeah. Anyone have a sandbox as a kid? It's always under the sand. Clay. Look guys, I have kids. I have built, I don't know how many sandboxes. We moved around a lot, but the sandboxes were awesome. Just throw the kid in there and they just play and they're happy. Okay. So I never put clay in the bottom of a sandbox. But after a couple of years, there was always clay underneath the sandbox. How's it get there? It's weird, but it's true. It doesn't matter where you dig a hole, clay is always under. It's always beneath. Here's why. Around here, the soil is pretty sandy, which means it's grainy, okay? There's lots of chunks. Even if they're small, you can feel them between your fingers, they feel gritty, okay? Clay, if you put it between your fingers like this, it feels like flour. It's very fine, it's almost slippery, okay? That means the particles that make up clay are smaller than the particles that make up topsoil. So if it lands on the top as dust, whenever that happens, okay, and then it rains, it washes the smaller particles between the bigger particles. So it always collects underneath the larger particles topsoil. So you always end up with clay underneath. Okay, that's how it gets there. Okay? So everywhere you dig a hole, you're gonna have topsoil, subsoil, just clay, and then beneath the subsoil, you're gonna get rock. Okay, Okotoks is awesome for this because you don't have to dig very far to see all three layers here. Okay, our bedrock, which is sandstone, is like in a lot of places in Okotoks right beneath the surface. Okay, I was trying to put in a fence in one of our houses when we lived in a different part of Okotoks, and when the backhoe, or when the bobcat came to dig the holes, there were a lot of holes that were this deep. Okay, he hit the rock, and I'm like, what are you doing? How am I supposed to put a fence in that hole? As far as I can go. And he's like, look in the hole. Sure enough, right on the sandstone. Couldn't go any further. Okay, so the bedrock here is actually quite close to the surface. All right, so what do you need to know about soil? You need to know the soil's got layers. Okay, you need to know the A horizon, or A layer, is the topsoil. The B horizon, or B layer, is the subsoil. And the C is decomposed or weathered rock, which we sometimes call parent material, because that's where the soil comes from. Okay, it's the weathering of that rock. That's why soil here is sandy. It comes from the sandstone. Okay? If you go further north where there's more limestone, the soil is different. It's finer, it's darker, okay? Because it's coming from different kinds of rock. Okay, so don't worry about the O horizon or the R. Okay, we're just concerned with A, B, and C. Okay, so dig a hole. This is what you're going to see: topsoil, subsoil, parent material, bedrock. Okay. Right, so around here, okay, we've got a pretty healthy A horizon on the prairies. Okay, lots of grasses every year, they die and they build up a good topsoil. So you got your black, healthy looking topsoil, got your subsoil here, okay, and then you got your parent material. So we got A, B, and C, okay, typical for around here. Okay, so the A horizon's got all the organic material in it, the decaying plant and animal material. That's the part where plants grow. Okay, you do see some deeper roots get down to the B horizon. Big trees can go that deep, maybe even get down to the C. Okay, but they're not going to go much further than that. Okay, B horizon, there's almost no organic material there because organic material is big. It's not going to wash down and collect underneath. So the B horizon is mostly the fine stuff, which is clay. Okay. And then the C horizon is parent material. So this is like just outside of Okotoks, this hole. Okay. I didn't dig this hole, it's somebody else's hole. I can't take credit for this. It's an awesome hole though. Okay, so you got your A horizon kind of here. Okay, you got your B horizon kind of in here. And there's going to be chunks of rock in all of them. Okay, but the bulk of the rock, okay, is down here in the C horizon. Okay, if you haven't dug a hole, got to do it soon. Okay, you just got to do it. All right, I think we will leave it there for today. We will talk about the 3 ways to transport energy on Monday, because tomorrow we're doing the climate graph activity, and on Friday we're going to finish it up. So that's what we're doing tomorrow. No quiz tomorrow. I haven't taught you enough stuff yet. So, okay, first quiz for this unit will be Tuesday.